So I was saying that this is an introduction to two-dimensional adeles. My talk is linked to Ivan's talk, Fesenko's talk that he gave yesterday. So Fesenko gave an overview of the theory and also the application of the theory. I will give a basic introduction to the subject. I'll try to construct the objects. And so especially I will focus on topological aspects. So this is joint work with Veronika Czerniawska, and also Fesenko yesterday mentioned two kinds of adeles. He mentioned geometric adeles and analytic adeles. And I just want to say that I will deal with geometric adeles and I will call them just adeles. Okay, so I think that we can go to the first slide. So the first slide is very general, and it is just to explain you the idea behind this talk. So adelic theory is divided into, in local elements and global elements. And then you can see that the theory separates in arithmetic geometry and algebraic geometry. But I want to present adeles like a unifying theory. So I just can say that these objects will be more or less the same. But what is the difference between arithmetic and geometry is the topology that we put on these objects. And I will be more precise later. So let's say that the constructions between arithmetic and geometry look very similar, but the topologies are different. And so for example, if you follow the branches of this tree, so the local elements, for example, for the field of rational numbers will be the p-adic numbers or R, and the global elements will be the adeles over Q. Okay, now let's start with a quick review of one-dimensional theory. And so this is already known, but what is done in the one-dimensional theory will guide us throughout the construction of two-dimensional objects. So local elements are just local fields. So just to fix the notations, so local field can be R or C. In these cases, we have Archimedean local fields. And of course, we have an absolute value that induces a topology. The third case is the non-Archimedean local field. And for me, a non-Archimedean local field is just a complete discrete evaluation field such that the reciprocity field is perfect. Notice that, of course, we have an absolute value and a topology associated. Notice that the first two cases, 1 and 2, the local field is always locally compact. Otherwise, in the third case, we have local compactness if and only if the reciprocity field is finite. And it is actually important. Okay, now let's go to the global theory. And global theory, we start with arithmetic, which is, let's say, the more natural. So you fix an arithmetic regular curve B, which is the spectrum of the ring of integers of a number field. And as you may know, this object is not complete, because if you take a principal divisor on this object, you take the degree is not 0. So you have to complete this object. I will call this completion with B hat. And what are the points at infinity? The points at infinity are just the set of embeddings of the number field to the field of complex number up to conjugation. Okay, so now we have a completed object. Some people call it compactified, but the point is not really topological compactification. It's just some way to complete this object, because we have problems with divisors. And now we have the definition of the ring of adeles. So notice that I call the adeles associated to B hat, but this notation is not common. Usually people call it the adeles over the field K. I've chosen this notation to emphasize B hat because I want to make clear that we have a geometric object, an arithmetic curve, and we are associating an adelic ring. So how it is defined? So this is very, very classical. So at each point, you have the local ring, you take the completion of the local ring, which is OB with a curly O, and then you take the fraction field. This is, of course, at finite places. At infinite points, you have the Archimedean local fields. So you have a correspondence for each point of your completed curve. You have local field, and then you take the restricted product of these local fields, which is basically a subset, actually a subring of the product. And the restricted product is very easy to describe. So it's made by all the tuples such that all but finitely many elements are integral. So they lie in the completed ring of integers. So as I was saying, in the case of points at infinity, you have the Archimedean local fields. And of course, in this case, we don't have the notion of ring of integers, clearly. Okay, so this is the ring of adeles, and you can also define the multiplicative group of adeles, which is defined similarly by taking the restricted product of the multiplicative structure. Okay, so far some easy definitions, but now we go to the interesting bits of the theory when we'll discuss about the topology. So as I said, the one-dimensional adeles are a subspace of the product. So we could ideally endow it with the topology induced by the subspace topology, so from the product. But this is not the right topology. On the other hand, we choose the restricted product topology, which can be defined, let's say, in two ways. Or you give explicitly the local basis around zero, or you can describe it as direct limits of locally compact groups. I mean, this is kind of standard, but if someone has questions, I can explain details later about the details of this topology. But I just want to say that it's not the product topology induced on the subspace of adeles. But why this topology is important? Because with this topology, then the adeles are locally compact group, of course, additive group. So why this is important? So this is important because locally compact groups, then we have Haar measures, and we can choose a normalized Haar measure on adeles, and this is in some references called Tamagawa measure. So it's just a choice of a Haar measure that makes calculations nice. Okay, so this is really important bit. So the topological aspects of adel are really important, and this is the first point where the theory is interesting. So we have a measure on adeles, and then the other topological property of the group, the additive group of adeles, is that it is self-dual. By self-dual, I mean that it is as group topologically and algebraically isomorphic to the dual group, so the group of characters. And just want to point out that this isomorphism is not canonical, because we have to choose a character and from here construct the isomorphism. The second topological property of adeles is that so clearly we can embed the number field inside the adeles and with the diagonal embedding. So we can see K as a subring of the ring of adeles. We can take the quotient, and the quotient is actually compact. And moreover, the field K again is discrete inside the adeles. So these are basically the three most important topological properties of adeles. So as I told you at the beginning, I want to focus now on the topological aspects. And these are the things that Tate used in his thesis to develop analysis on the ring of adeles and on adeles. But some of these properties actually were already known by Iwasawa and also Chevrolet. And so these properties are actually crucial to the study of the Riemann zeta function, as Ivan explained yesterday. And the point of doing two-dimensional adeles is that actually we want to get similar properties, but for two-dimensional adeles, in order to study the two-dimensional zeta function that was defined in the talk yesterday. Okay, so this is what I wanted to say about arithmetic global theory, so definition of adeles and topological, most important topological properties. Now let's go to the geometric global theory. So this is how the theory of adeles starts being, unifying in the sense that we can treat function fields and number fields almost the same way, but with some topological differences. So now we fix a regular projective curve of a perfect field K. We have to choose a perfect field K because we want local elements to be local fields in the sense of my definition. Okay, and now you have again the ring of adeles. So you basically have the local ring, you complete it, you take the fraction field, and then you have the restricted product again. So here you can notice immediately the first difference. And the first difference is that here you don't have Archimedean local data. So here everything is non-Archimedean. And again, you have the group of adeles. So here the formal construction is actually the same. But as I mentioned earlier, the important difference is in the topology. So again, we have the restricted product topology on adeles. But in this case, if the base field is infinite, the ring of adeles is not a locally compact topological group. But there is a way to deal with this. So the ring of adeles is a vector space over the base field. And let's say, so for groups, we have Pontryagin theory of local compactness. Otherwise, for vector spaces, we have Lefschetz theory of linear compactness. So these theories are kind of parallel. So what you get from Pontryagin duality, Pontryagin theory, you have more or less the same in the theory of vector spaces in this theory of Lefschetz linearly compactness. So we have that the ring of adeles is linearly locally compact vector space over K. I'll try to explain more. So let's say you have a vector space with a linear topology, and we say that it's linearly compact. Well, there are many ways to define this object. Maybe the quickest is the following. Maybe it is the least intuitive, but maybe it's the quickest. So we have this vector space. So we say that it is linearly compact if it is projective limit of vector spaces of finite dimension with a discrete topology. Okay. If this happens, we say that the space is vector space is linearly compact. And of course, it's linearly locally compact if it contains an open vector subspace, which is linearly compact. So this is almost similar to Pontryagin theory of local compactness. So again, so similarly to the results that we have in the thesis, now we get the followings. So the ring of adeles is self-dual, but again, self-dual in the theory of vector spaces. So we have to be careful about what is. Of course, we have another notion of dual, and yeah, there are some formal differences. So the quotient now is a vector space which is linearly compact in the sense of my description I gave earlier. And also K is discrete in the ring of adeles. Okay, so as you can see, formally we have the same properties I mentioned earlier for number fields, but here we're talking about vector spaces. Okay, and now we have just a remark. So we have a natural map from the adeles to the group of the divisors, and actually we can lift the notion of degree of a divisor to the adeles. So this can be done also in arithmetic case, but we have to deal with arithmetic divisors or replete adeles. So it's I mean the same lift can be done for the arithmetic case. Okay, now my quick review of one-dimensional theory from the topological viewpoint is finished, and I go finally to two-dimensional theory, which is the real focus of my talk. So we have to define the local elements. So local two-dimensional elements. So imagine you have a two-dimensional local field, then you take the residue field. This field is again a complete discrete population field. And you repeat this process, no? When you do the residue field, it may happen that the residue is again discrete population field. So at the end of the day, you get a finite sequence of complete discrete population fields, and you have you can put an index to residue fields. Just in my slides is I. Okay. And now we get to the fundamental definition of my talk, which is the n-dimensional local field. So n-dimensional local field is a complete discrete population field. So you have this sequence of residue fields, but when you get to the field of index n-1, this must be a local field in the sense of my first definition I gave today. Okay, if this last field is Archimedean, then the whole field F will be called Archimedean. And of course, you also have the notion of mixed characteristic. So before someone interrupts me with a question that I can imagine, I want to just write something about this definition. So this definition of dimension is not actually well defined if posed in this way. So imagine you have, okay, start my pen again. One second. Okay, so imagine you have the field, the Laurent power series of SC. So on one hand, this is two-dimensional because if you take my definition, you have the residue field, which is C, and this is Archimedean local field. So this is two-dimensional. But on the other hand, of course, the Laurent power series is a complete discrete population field. So it is one-dimensional. So one could fix this thing by saying that one takes the maximum of the possible dimensions. But the point is that I don't want to do that. And I'll explain why. So if you are in the theory of curves, C of t, this field, appears as local field attached to one-dimensional object. In this theory, this will be one-dimensional with the topology induced by the evaluation. We will see in a moment that this field appears also in two-dimensional adeles. And this theory, I want to put another topology. So in the theory of two-dimensional adeles, this object will be two-dimensional because it comes from a two-dimensional object. So actually, it's the topology that we put on the field that chooses actually the dimension. And this is why in my definition, I didn't say that we take the maximum of the dimension. Because if we come from curves, I will say it's one dimension. Now, if we come from surfaces, I will say that it is two-dimensional. Okay, so I hope that this issue is kind of understood. And I go now to the classification theorem. So you take a two-dimensional local field, and there is a theorem, which is the classification theorem, that says that just one of these options can happen. So I will explain this table. So we have some names, so geometric, arithmetic, and Archimedean, that will be clear soon, but geometric means this field appears from surfaces. Arithmetic means that this field appears from arithmetic surfaces. And then the Archimedean fields appear from completions. These numbers here that you can see, these are the characteristics of the residue fields. Okay, so we have here, if you see my pointer here, it is the trickiest one because it's mixed characteristic. So now we'll describe these fields, and one of them is the field that maybe you don't know, and I will have to explain. So the first case, we have double Laurent power series, where the field, base field is perfect, and this is okay. This I will explain in a moment, the second one. The third one is the Laurent power series. So Kp is just a finite extension of the p-adics. And then, as I told you, we have the Archimedean fields that here will be considered as two-dimensional. So before continuing, just want to explain this field with curly brackets. So let's say that we go with Qp, okay? Qp of T is the set of power series which are infinite on both sides, okay? Where the coefficients are p-adic numbers. Then you have the infimum of the valuations of the coefficients is a number, it's a well-defined number. And then you have the limit when the index go to minus infinity of the coefficients goes to 0. Okay, this is a field, and you can prove this is a field. Then you have an evaluation, which is kind of easy to define. So the valuation of a power series, which is again infinite, is just the infimum of the valuation of p-adic valuation, and this number is well defined, of course. So you can show that this field is complete with respect to its valuation, and actually you have this chain of residue fields. So the residue map is the obvious one in coefficients. So you have this is the field. The residue field will be the Laurent power series over T, over Fp, and you can see here the change of characteristic. And the last residue field is the finite field. Okay, so you see 0, P, P, as explained in my table. Okay. So now another crucial aspect. So we have these fields, and as I explained earlier, we don't want to consider the evaluation topology, these fields. Why? So these fields have a level structure. So, but if we put the evaluation topology, the residue field might happen to be discrete inside when it can be embedded, can be discrete inside the whole field. So basically, if we put the evaluation topology, we forget about the fact that the residue field is again complete discrete evaluation field with its own topology, so cannot be discrete. So we have the notion of higher topology. So let's say that you have here an abstract two-dimensional local field. Then with an isomorphism, you put this field in correspondence with one of the fields in this table. And then there is a way to put a topology on the fields in this table, which is called a higher topology. And then through the isomorphism, then you pull back your topology on the original abstract two-dimensional local field. Okay? So in general, this topology depends on the isomorphism, on the parameterization, but in some cases it doesn't. So for example, in the case of mixed characteristic, this topology doesn't depend on the isomorphism you choose. Okay, so but the point is that if you want to correctly put a topology on high local fields, on abstract local fields, high local fields, you have to go through this table. Okay, so this is the theory of abstract and two-dimensional local fields in, of course, in a very short way. But now I will tell you how to associate two-dimensional local fields to schemes. And this is crucial because when two-dimensional local field is associated to a scheme, then you can put this higher topology in a canonical way without passing by the isomorphism to a field in the table. Okay? And so let's fix our scheme. That is a two-dimensional Noetherian integral regular scheme. And now I'll go through some easy definitions, I mean, just notation. So with curly O of X is the completion of the local ring at points. This is the fraction field of the completed local ring. I put prime because in the theory we use this field less, but what we will use, and probably it will appear in next talks, is this field, is this ring. It's not a field, sorry. It's the ring generated by the OX and the function field of the scheme. And of course, this is smaller than the fraction field of the local ring. So this is data associated to a point, a closed point. Then you have an integral curve, and we put OY is again the completion of the local ring at Y. Y, I mean, identify the curve with its generic point, and then we also take the fraction field, and it is KY. Just for a moment to switch maybe for the last time to my tablet to tell you a thing. So now the general idea is the following. So if you have a curve, we say that we have to each point we have local data, which is K of X. On the case of schemes, we do this operation here. So we have a point, small x, then we take a curve passing by a point, it is small y, I'm talking about integral curves. Then to the couple xy, I associate a local element, which will be kxy. So for each couple point curve passing by that point, I will have a local element, kxy, and this will be in general finite sum of two-dimensional local fields. Okay, because the issue, we will tell you in a moment, is when you have some singularity here. But now we'll tell you. So in the one-dimensional theory, we have points and local data. Here we have couple points and curves, and then we associate local data to those things. Okay, I can go back to my slides now, and okay, now this is the issue about singular points here very quickly, because just technical detail. So when you complete, you have a canonical map from the spectrum of the completion, and also when you have a curve passing by a point, you have an ideal corresponding to that point. Then you can pull back this ideal through this morphism phi. And the inverse images of these ideals are called the local branches. So the number of local branches tells you about the nature of the singularity. So for example, in this case, we have simple nodes. So we will have two local branches. If the curve is moved on the points, then you have one local branch, or even you have a cusp, where you have just one local branch. So the number of these local branches tell you about the nature of the node, to be precise. And this is just a picture. So okay, so now we fix a point, a curve containing that point, integral curve, and then also we fix a local branch. And then we have the local data kxz that will be obtained this way. So you take the local ring, you complete, then you get curly OX. Then you localize at this prime ideal, Z, then you complete this localization at the maximal ideal, and then you take the fraction field, which is another localization, basically. So again, it is the process of completion localization, which is iterated twice. And it turns out that this is a two-dimensional local field, and the ring of integers is denoted by OXZ. Okay, now the crucial point. So completion and the localizations can be described as direct or inverse limits. And it is well known that you can carry the topologies through direct and inverse limits. So you take initial or final topologies. And by doing this, you can finally get a topology on KXZ, which is actually the higher topology that I was searching for. And in the next slides, maybe there will be some more detail about these topological aspects. But again, just to be precise on this, so local fields arising from geometric objects, so couples, points, and curves, have a canonical topology. In general, if you take higher dimensional local fields, the topology depends on the isomorphism with the table I showed earlier. Okay, so now there is a diagram. It's just for notation. Actually, you can see here. So this is the local field, first residue field, and final residue field, which is in general a finite extension of the residue field at a point. And okay, and finally, as you can imagine, I can define the local object I was talking about. So for each branch, you take the direct sum over the local branches. And of course, if your curve is smooth at the point, or even if you have a cusp, these products are just made by just one element. Okay, so in one line, KXY is the local data attached to the couple point curve. Okay, now we see in an abstract way how to obtain a two-dimensional local field. Now we distinguish the two cases when we have algebraic surfaces or arithmetic surfaces. So in the first case, remember the base field has to be perfect. You have Laurent power series. The second case, so we have an arithmetic surface, so which is a two-dimensional scheme over the spectrum of integers of a number field, and the morphism is flat. You can put all nice properties of this morphism. So in the horizontal case, you have this Laurent power series over Kp, and otherwise in the vertical case, then you have the field with the curly brackets. So vertical case, I mean when y is a vertical curve. Remember that on arithmetic surfaces you can have just two cases. And of course, if your point on the surface goes to the base through this map and goes to B, the local field of the base embeds into the local field on top. So this is an important difference between algebraic geometry and arithmetic geometry, and the most difficult case to deal is with the vertical case. Okay, the constructions are more complicated. Okay, now the slide I promised you, so the slide about local topologies. So, okay, I forgot to tell you that actually higher topology can seem weird. In fact, two-dimensional local fields, when you put higher topology, are not topological ring. It means that the product is not continuous as function of two variables, but it's just continuous in each single variable, and moreover, it is sequentially continuous. But it's not continuous as map of two variables. So ring with these properties is called semi-topological ring for obvious reasons. So in particular, a topological ring is a semi-topological ring, but we will carry these topology arguments in the category of semi-topological rings because we have this issue with continuity of the multiplication. So here we have two operations, C and L. C stands for completion, L stands for localization. It explains how to carry the topology that we want through localizations, completions, and localizations. So as I told you, it's about initial linear topology and final linear topologies. So as I told you, it's something about category theory. And here how it goes. So you start with the local ring. So local ring with the adelic topology. This is of course a topological ring, but it's in particular semi-topological ring. So in this category, you can carry all these operations CL, as explained here, and you get a topology on the two-dimensional local fields K, X, Z. So this is more or less more precise definition when I said that we can carry this topology in a canonical way. So I think that it is what I want to say about the local data. Okay, now we go to the global theory, finally. If we have a surface of a perfect field, the adelic ring is the result of two restricted products. So for curves, for arithmetic curves, we did one restricted product. So in this case, we have like two indices, so points and curves. So the idea is to do restricted product twice. So we do it once, we fix a curve and we do restricted product along points, and then we vary our curve. Okay, so as I was saying, the first one is when we fix a curve and we let the points vary on our curve. So we get this object I called a y, which is this. So is the Laurent power series over the ring of adeles associated to y. So to be precise, to the function field of the curve y. This can be embedded in this product, but this is, let's say, the semi-local object. So this is the result of the first restricted product. This is quite simple. So it's Laurent power series on the ring of adeles of the curve. The second, before second restricted product, we can shift this by putting an index here in the obvious way. And then we have the second restricted product when we allow all the curves vary. And this is more similar to the original restricted product that we had in dimension 1. So you take a subset of this product and you allow almost all elements to be integral in this sense. Okay, so almost all Laurent power series will be actually power series. So, and this is the ring of adeles. So again here, of course, there is the issue about what topology to put on these adeles. But this two restricted product can again be seen as inverse or direct limits. So you can start from the local topologies that now we have here, and you can carry in a categorical way with final or initial topologies your topology in here. Unfortunately, so here, so you have vector space over the base field K. This is not locally compact. It's not even locally linearly compact in the sense of vector spaces. So, this is the the main difference with the one-dimensional theory, that the topology of two-dimensional adeles is a bit more complicated. So here, what happens that you have a rational differential form. You can define a pairing from the adeles to the base field K. And this pairing can be obtained by taking the residue and composing with the multiplication. So it's basically taking at each two-dimensional local field the residue. The residue will be the coefficient of degree -1, and then you put all this data together with the sum and the shift. I mean, this you can find in Fesenko's paper. And so you have this pairing, and in analogy with what you get in the thesis, we obtain the following theorem, which is due to Fesenko's paper of 2015, that A of x is self-dual in the theory of vector spaces. So again, I'm considering A of x as vector space over K. The quotient with this, so this is the orthogonal complement with respect to this pairing. So it's the orthogonal complement of the function field. This is linearly compact. Notice that in the case of curves, this orthogonal complement corresponds to the function field. So this is why you don't get this orthogonal in one-dimensional theory. And moreover, the function field is discrete in the adeles. So again, you get exactly what you expected in two-dimensional theory, at least from in the topological setting, in the topological framework. So this is basically the two-dimensional versions of the results I mentioned at the beginning of my talk for algebraic curves. So I started with geometric theory because in dimension 2 is easier. Things are a bit more complicated in the case of arithmetic surfaces. So here we have x over b, which is an arithmetic surface. So this bold curve is the generic curve. As you may know, again, this object is not complete. So we have to complete with the so-called fibres at infinity. So these fibres at infinity are obtained by, let's say, the base change of this scheme along the embedding sigma with respect to the fields of complex numbers. So to be clear, this curve is a smooth Riemann surface. Okay, it's a Riemann surface. And what happens? So here you can start doing an Arakelov theory of intersections. So it happens that, let's say that you have a horizontal curve. So a horizontal curve meets the generic fiber at a point. We assume the horizontal curve is again integral. And then the base change gives by base change, again, a map from the fiber from the fiber at infinity to the scheme. So the result is that this point here will have some counter images here. And these 2 points here, there are 2 points, may be intended as the intersection of the horizontal curve with the fiber at infinity. So let's say that the horizontal curve can be completed to the curve, can be completed by adding to the curve y these 2 points, which are the intersection points with the fiber at infinity. Of course, these curves are not physically meeting, but by intersection, I mean that they're related by this map. Okay, so of course, not all points from the curve at infinity arise as intersection points from horizontal curves, but just algebraic points. Okay, so let's say that on the fibers at infinity, there are some points that arise as intersection points with horizontal curves. Okay, so now to our picture, basically we added 2 possible couples point curve. So let's consider the curve at infinity. So you have a point lying on a curve at infinity, and you have the couple point lying on the fiber at infinity. And to this object, you add this local field. So Yeah, so here I said that you have a Riemann surface, but if the embedding is real, here of course you have a curve over R. So of course this is a Riemann surface if the embedding is complex. But in general, you have everything over this field K sigma, which can be real or complex depending on the nature of sigma, of course. So I was saying that to the couple point lying on the horizontal fiber, on the vertical fiber at infinity, you have this Laurent power series over R or over C, but there is another couple point curve which wasn't noticed in the past. That this is actually the new bit of this completed adelic theory. That it is when a point lies on a horizontal curve. There's this other let's say flag. By flag I mean couple point curve, which is point at infinity lying on a horizontal curve. So this point lying on Y. So in this case, we have this KP completed Y that will be exactly another copy of this field. So the bottom line is that with adding the fiber at infinity, you can have a double copy of Laurent power series over R or over C. And this is the two-dimensional analog of adding the infinite points on the base arithmetic curve. Okay, so this is the important bits on completed adelic theory in two-dimensional arithmetic setting. Okay, and so just a quick remark. So we have to put a topology on this field, which is not the valuation topology, because if we put the valuation, so for example, imagine you have C here, to be clear. So if you put the valuation topology, then the field C will be discrete inside the Laurent power series. So we don't want this topology. And so we want to consider this object as two-dimensional. So this topology can be described in several ways, but just to be coherent to what I said earlier, so obtain this topology as a process of completion and localization, you basically you do this. So here just say that I want to emphasize the fact that this is two-dimensional. So basically you put you have a topology on the polynomial ring, and you put this final topology, and then when you can localize and apply the same. I mean, you can complete and localize, and C and L are the same operations I explained earlier. Okay, so with this approach to the topology, you get some topology which is not the valuation topology, and the topology of the residue field is the Euclidean one. So we start with the topology, the one-dimensional topology on C or R, which is not actually the discrete topology, of course. So we start with the topology of local field, because we want to remember that the residue field is a local field and not a discrete field. Okay, this was just a remark. And okay, so now we want again to construct adeles by restricted double restricted product. So ideally, we would do the same process we did for surfaces. So we do the first restricted product by fixing a curve, and then by letting the curve vary. But here there is the first obstruction, is that this definition here I put F, which means finite at adeles, because when the curve is horizontal, of course we're missing the points at infinity of the curve. So the point is that this definition holds when you have horizontal curve. But this definition is not longer true for vertical curves. So for vertical curves, we have a more complicated and abstract version of this object, which is not so explicit. And this makes things more complicated. And this is why at the beginning I said that the case of vertical curves is trickier. So we need a more abstract definition of a y, which is possible, but I cannot tell the details about it in my 10 minutes remaining. So I just say that the idea of definition is similar. I mean, the property of the objects are similar, but it's not so explicit. So for the moment, you just to accept that it's similar. Okay. So let's say that we have this AY for horizontal and vertical. Then we have to complete AY and go to AY bar. Remember that AY bar is the completed version, so Y bar is the completed curve. And we do it by adding the local data at infinity, as I explained you 2 slides before. So these are the Archimedean local fields. And finally, once that you do it, basically you get the A bar, which is not yet the final version of adeles. So this is the second restricted product, but this is the version of adeles that takes in account the completed curve. Okay, so in this version of adeles with the bar, basically we are considering completed curves. So because horizontal curves must be completed. And finally, we have the ring of adeles. So you take this A bar, defined this way, and then you add the adeles associated, the one-dimensional adeles, but with topology considered two-dimensional way of the fibers at infinity. This is the final version of completed adeles. This is why I put the hat here, because I'm considering the completed surface in the Arakelov sense. And what I want to say about this is that, again, the topology is naturally induced through this operation. So the topology can be, again, put in a canonical way of these adeles from category theory. And again, this topology is very far, this group is very far to be locally compact. And in general, a measure, it's not possible to define a measure here, even an extended measure. And this is why Fesenko introduced the notion of analytical adeles, because here it's impossible to carry a functional analysis. Let's say that this space is too big. Okay, so similarly to the case of surfaces, for rational differential form, here we have a one form because the relative dimension is 1. So this arithmetic surface is a relative object. You have this pairing. Now we'll say more about this pairing. So these are adeles. This is the character, which is defined in this way. So locally, you take the residues of these two-dimensional local fields. So for example, here, this point X, you have two-dimensional local fields, the one arising from the vertical one and the one arising from the horizontal one. And then you have two residues, you take the sum. Then you have the residue coming from this point here. So you push it back to the base, and then you take so here you go to the adeles on the base, and here you take characters of one-dimensional adeles, and you go to the unit complex unit circle. So in this way, you obtain a map. So of course you have to compose with multiplication. Here you have a map, and what happens? So happens that this map, this map here is sequentially continuous. Actually, can show that it is continuous, and this gives self-duality of adeles. So one result of my joint work with Veronica is that the ring of completed adeles is self-dual. So we recover the topological property that we wanted for two-dimensional adeles. So I just tell you the strategy of the proof of self-duality. So you can reduce everything to show the self-duality of the semi-local objects. And when y is horizontal, you use this explicit expression of ay, and basically you lift the standard character, or the character that gives self-duality of the one-dimensional adeles. You can lift this character to this space here and show that this character gives self-duality. Okay, this is more or less standard. The tricky part is when you have vertical curves, because when you have vertical curves, this lift is not obvious. But let's say that it can be done with a bit more work, but more or less it works by lifting the one-dimensional theory to this object here. So now I just want to tell you about some work in progress to finish my talk. So we're working with Fesenko and Veronika Czerniawska on compactness of this quotient and the discreteness of the function field inside the ring of completed adeles. And then a crucial fact that I will mention, so these spaces, A01 and A02, are just B and C. So these are the two spaces B and C that Ivan defined yesterday in his talk. We showed in our work with Veronika that these spaces are self-orthogonal. So this is very important property, because self-orthogonality of these spaces are a stronger version of the reciprocity laws on surfaces. So reciprocity law on surfaces tells that when you fix a point and you vary the curves passing by this point, the sum of residues is 0. Or when you take a curve and you vary the points along this curve, again the sum of residues is 0. So I'm talking about algebraic surfaces. So when you have sums. In arithmetic surfaces, it's a bit different because you have products, and instead of 0, you have 1. But these reciprocity laws hold also for surfaces. And these are actually important, really important to prove these things here. And I think that with this, I can finish my talk.